Welcome back, friends. We were looking at bilinear covariance in the Dirac equation essentially. Along the way, we introduced what are the scalar currents, vector currents, and tensor currents. And then we started looking at examples where do they appear. And along the way, we introduced the so called the Dirac Lagrangian, which is the most important thing, which is okay. The Dirac Lagrangian we have seen to be consisting of uh, a simple form which is given by this particular equation. This is the Dirac Lagrangian. Okay, there are I should mention that sometimes you also see lecture a any textbooks and everything, not in this particular fashion, but also the Dirac Hamiltonian given in terms of alpha and beta matrices essentially. Okay, so alpha times so what we have seen earlier essentially, so we can write alpha times p times beta times m. That also is called as a Dirac Hamiltonian in some textbooks and so on, so essentially. Okay, but what we will stick to as a relativistic this way of writing is more consistent, that is also correct, that's not incorrect essentially, but this way of writing is more convenient when we introduce interactions and when we introduce interactions and this makes it life easier essentially. Okay, so we write it in a simpler fashion, more convenient and very nicely. So this is called the Dirac Lagrangian, and from this we can easily derive the Euler's using the Euler's equations of motion, where the variable or the derivation with respect to the field psi, you can get it del by del psi gives me this I del slash minus m psi is equal to 0. This is your Dirac equation. So you get back your Dirac equation from this Lagrangian. So there is no problem. But then so you saw that the Dirac Lagrangian consists of two terms. One is the kinetic term and another is the mass term. And the Lagrangian should always be real and a Lorentz scalar. And so the interactions of this Lagrangian appear as various forms, as various bilinear covariants. We were looking at two particular examples which are very important, which we will keep coming back to them in the coming lectures essentially. So one of them is the so called Yukawa interaction, in which we introduce a scalar field, scalar particle which is phi, and so you add for the Dirac Lagrangian plus let me call it as YL Yukav. Okay, so in this case you introduce the introduce not only just the Dirac Lagrangian, but also introduce the scalar current. The scalar current psi bar psi is invariant, and if you want to multiply another invariant quantity, the scalar field or the scalar wave function is an invariant quantity. You just multiply these wave functions and you call this as an interaction period. Okay, you just multiply this current with a scalar wave function, and this you call it as a because the interactions are always current. So this is an interaction term. So and there is a reason why you this particular thing works essentially. If you do as we will see in the coming lectures, what we will do, okay, I can just tell you the motivation why this is called the Yukawa interaction. In the non-relativistic reduction, if you do a non-relativistic reduction of this particular theory, you end up having ordinary quantum mechanics Schrodinger equation with a Yukawa interaction, with a Yukawa potential. So that is this is the relativistic form of a Yukawa interaction. The relativistic form of Yukawa interaction is, because you cannot have potentials in relativistic theory, that we have seen it right from the Klein-Gordon equation, you have to introduce particles you have to introduce particles, and in the when you to go to the non-relativistic reduction, you have Schrodinger equation, a particular form of Schrodinger equation, because when you do the non-relativistic reduction of Dirac equation, you get Schrodinger equation plus a Pauli term, okay, plus Yukawa interaction. Essentially, Yukawa interaction is not really sensitive to the spin of the particle because it's a scalar interaction, but there are other kind of interactions which are which can be sensitive to the spin of the particle, like if it's a vector like interaction. So anyway, you get a Schrodinger equation with a Yukawa like potential. You can get a Schrodinger equation with a Yukawa like potential, and that is the reason why the relativistic form of that particular Lagrangian is consists of a scalar particle with a Schrodinger Klein-Gordon what do you call a Klein-Gordon Lagrangian, along with a Klein-Gordon Lagrangian. And I just showed you a graphical interpretation. Suppose if you have an electron, which psi is the wave function of the electron, it comes in and it goes out, and this phi is nothing but your mediator between these two electrons essentially. So this kind of interaction, which is a scalar like particle, which is being exchanged between the electrons, is called a Yukawa interaction. A similar thing can happen, but if you have electromagnetic interactions. So here we have written the Lagrangian of QED, quantum electrodynamics. This is a Lagrangian which will keep coming in essentially. So this is nothing but the Dirac field, essentially Dirac wave function, Dirac Lagrangian, okay, multiplied where it has a vector like current which we just introduced in terms of the bilinear covariance, a vector like current multiplied by the photon field, photon wave function, which is A mu, which we introduced when we are doing the Klein-Gordon field essentially, and the kinetic terms for the photon wave function. The kinetic terms are nothing but F mu, which give you the photon wave equation. This F mu give you the free photon wave equation. So you have a free electron wave function, a part which gives you electron wave equation, a part which gives you the free electron photon wave equation, and in between this part is the interaction part, where you just multiply these wave functions in a Lorentz invariant fashion in terms of currents. Because the photon is a vector like particle, it can only couple to a vector like current, and that is the reason why we need to know what are the currents of the Dirac equation, what kind of Lorentz invariant currents which we can write down, okay, for using Dirac wave functions essentially. And we have seen that you can write a vector current with using two Dirac wave functions, and this vector like current can couple with another vector like current, which is the photon wave function. So this is nothing but your interaction, okay. So on the right hand side you have a free photon wave function, left hand side you have a free electron wave function, in the middle is the interaction, and this is a Lorentz invariant interaction because you have to write it down in terms of, because we are in relativistic field theories, essentially it has to be Lorentz invariant, and the only way the photon which transforms like a vector under Lorentz transformation can couple to a electron is through a current, vector like current of the electron, because it and we had, okay, because it is the vector like current is only possible with psi bar gamma mu psi. Remember, psi's are not vectors, they are spinors, and They are Lorentz spinors. They are spinors. They transform as spinors. They are completely different. The space is completely different. Their vector space is completely different. Whereas gamma mu transforms as a Lorentz vector. So that's the reason why we need to put in gamma mu so as to make this interaction possible. And this interaction is nothing but your quantum electrodynamics interaction. So this is how you introduce electrodynamics into quantum to Dirac wave function, which is an electron. Electron has spin half. As I said, Dirac equation corresponds to spin half solutions, and whereas the scalar field corresponds to spin zero solutions. Okay, so an example would be an electron coming in and going out in time, and while going out it gives you sees another electron at some distance and emits a photon which is absorbed by the other electron essentially. This interaction can be described by quantum electrodynamics by the above Lagrangian, which is the Lagrangian of the QED. We keep coming back to the QED Lagrangian again and again. So these are the two examples we have seen of the interactions. Now, but let's go further as a in understanding the various representations okay, of the Dirac theory. But before doing that, now the question arises, Dirac equation also has so what we saw was that Dirac equation also has antiparticle solutions exactly like Klein-Gordon equation, essentially exactly like Klein-Gordon equation. And then when we introduced interactions in the Klein-Gordon equations, we ended up having all kinds of funny behavior. One of the things was because we introduced static electromagnetic potential, and then it had something called the Klein-Gordon Klein paradox. Okay, and then we introduced we also had something called the Zitter-Bitter-Wiegang. We have rapidly varying currents essentially because of the around the potential. It generates particle antiparticle solutions and so on. So these problems, do they exist also? Whatever problems which we have seen, do they exist also in Dirac theory? Okay. Antiparticles. Okay, we have seen both these features, the Klein paradox and Zitter-Bitter-Wiegang, do exist in Dirac theory. And the answer is a resounding yes. Okay. Now remember, both this Klein paradox and Zitter-Bitter-Wiegang are associated while we are treating potentials as non-relativistic potentials essentially in a relativistic theory essentially. So if you introduce a step like potential in, okay, now compared to this, here we introduced the photon field as completely relativistic picture. The interactions are introduced in a completely relativistic fashion. Okay, in a completely relativistically invariant fashion. Okay, now interactions are introduced in a completely now suppose if I say I don't do this, okay, and that is the reason why I introduced them in the Klein-Gordon field itself, essentially, because I think the way we typically do is essentially we do the Dirac theory and then we do the Dirac C and all that business. Okay, I'll come to that in a second, essentially, but I wanted to introduce the problems with the introducing directly trying to solve with potentials with the Klein-Gordon field, because the same problems also exist with the Dirac theory, because we already introduced we are already introduced to that, so we just had to repeat it. We just say that the problems are just a repetition, essentially. The solution, the answer is yes. Okay, the short answer, essentially, the short answer is yes. So they do exist, essentially. Now let's say why do they exist? Because again the same thing. Now you're introducing, let's take a step potential. Same example as in KG Klein-Gordon Klein-Gordon case. So in the Klein-Gordon case, what we did was we considered a step potential centered at, so we had a potential V0. Okay, this is at x is equal to 0. Say for example, we had a potential of this particular type. So with a hat of this particular kind. So this potential has, so V of x is equal to V0 for x greater than 0, is equal to 0 for x less than 0. So this is the definition we introduced. Okay, and then we introduced this V0 into the Dirac, into the Klein-Gordon equation. In the same way, let's try to introduce this in the Dirac equation. So the Dirac equation, suppose if I do the Dirac equation, it is I del slash minus m psi minus V of x psi of x 0. Okay, let me write down explicit. Okay, now the left hand side is the Dirac equation, and here I introduce the potential. Now the moment, okay, at the equation level you don't really care about Lorentz invariance or something, essentially, but okay, at the equation level, so you just introduce but at the back of my mind I know that this is not coming completely relativistic theory. like what happens if you have bilinear covariance. So in the case of bilinear covariance, I am introducing in a relativistic theory, and if I do the non-relativistic reduction, I get Schrodinger equation. I don't get Dirac equation. I get Schrodinger equation with the electrostatic potential essentially. Whereas in this case, I am putting the relativistic form of the wave function for the electron. So I am partly doing it is half relativistic, half non-relativistic. So this is the kind of situation you are having essentially. So you are having okay a potential like this, a step potential on this particular fashion, and repeat the same exercise exactly like what I did in the case of in the case of in the case of the Klein-Gordon field essentially. So you can start off by considering the same thing, and then now you put in a wave function coming on the left. Now consider only positive energy solutions. Consider only positive energy solutions. So in this case, these are just a u of x essentially. Slight complication is that instead of psi plus, which we considered for the Klein-Gordon equation, you have the spinor essentially. So the wave function is essentially u of x. So u of x comes in, okay, and goes, scatters, okay. So then you have a reflecting wave on this side and a transmitting wave on this side. Now you try to compute the the reflection coefficient and transmission coefficient essentially, the reflection coefficient and transmission. Now as long as the potential energy is much smaller, as long we have considered the several cases, right, the same thing will appear essentially, weak potential that means the potential energy is say much smaller than 2m0 c squared essentially. That means it does not have the energy to create pairs or something essentially. It does not have the rest mass of the equivalent to the mass of the electron essentially, this m0 square or me, let me call it as me, let's call it a square. In that case you have the reflection coefficient plus the transmission coefficient should be equivalent to 1. This is satisfied. But in the case of the strong potential or intermediate potential essentially, if you have this kind of scenario, what happens is this relation is no longer satisfied essentially. You end up having absurd answers, okay. You end up having absurd answers exactly like in the case of the previous case, because in relativistic theories again Klein paradox. So your paradox is appearing again, essentially your Klein paradox appears again, okay. And so you repeat the same exercise what you have done for the Klein-Gordon equation, and you will end up having the same result here also essentially. So you cannot escape the problems created by negative energy solutions in this case. The reason is because in the when you are dealing with this, the Dirac equation always comes together. The Dirac equation always comes together. The wave function comes together with both positive and negative energy solutions. It has the the potential couples both the positive and negative energy solutions. So if you even if the moment you throw away one particular set of solutions and try to solve this Dirac equation, you cannot throw away the negative energy solutions completely. You can only start, the initial condition can only be taken as that you only start with only the initial. So you may choose your initial condition such that you only have a positive energy solution, but while propagating, while transmitting, essentially, while the moment the interaction part happens, the interaction part couples both the positive and negative energy solutions, and if the potential is strong enough, this will create problems essentially in the reflection and transmission coefficients. Okay, so this is a very crucial. So the negative energy solution problem will not go away in Dirac theory. It will repeat the same thing. It will end up being the same thing. Okay, and I advise you to read the some very nice papers. I can meaning on in American Journal of Physics on the Klein paradox for the Dirac theory. They are very well written essentially, and you can look into them in more detail. Now the same, and this Zitter-Bitter-Gang also just goes through exactly like what happens in the case of in the case of the Klein-Gordon field essentially. So the Dirac equation doesn't really solve that negative energy solution problem essentially. So both the cases of the both the paradoxes essentially are associated with the Dirac of the Klein-Gordon field, essentially the Klein paradox, as well as the Zitter-Bitter-Gang, okay, still exist. Now, how does so Dirac proposed a solution to the negative energy states, solution to the negative energy states. So what happens to these negative energy states? Okay, so this proposal is the origin of antiparticles. We have been assuming all through these lectures that the negative energy states are nothing but antiparticles of this theory, but Dirac proposed this thing entirely by building a theory around it. Okay, and this theory is called the Dirac sea and the introduction of antiparticles essentially. So what did Dirac say? Okay, Dirac thought meaning was worried again. So the problems of negative energy solutions. So okay, so the problem of negative energy solutions exist also in the Dirac theory, and it continues because we see that the Klein-Gordon, as we have seen the Klein paradox and everything. So Klein paradox, everything. So what he said was, so he proposed that all the negative energy states in nature are completely filled under the vacuum. So imagine that on the y axis you have energy and x axis are essentially labeling of the states essentially. So the negative energy states would be below the x axis. So below the x axis all the states are filled essentially, they are all filled because they don't have they are below the lowest energy state. Okay, they are below the lowest energy state essentially. So this he called it as the Dirac sea. So this is called the Dirac sea. Okay, so this is your lowest energy state, this is your ground state of a quantum mechanical system, and the negative energy states are below the ground state, so they are all filled up. They are all filled up in nature. They are all occupied essentially. They are all completely occupied. They are all completely filled up essentially. And these are all also electrons. Electrons fill up even all these things. These are also electrons essentially. Okay, let's imagine that these are all electrons. But what happens once in a while, there is a photon comes in. Photon comes in, and this has energy. The photon has energy greater than 2 times mass of the electron c square essentially, 2 times the mass of the electron. So this is the lowest state, second lowest state, third lowest state, and so on, so essentially. Okay, so if it has energy greater than 2 times mass of the electron, it kicks out one of the electrons in the negative energy state, and this negative energy state comes out. This negative energy state comes out with positive energy, and here there is a hole. This hole is absence of the electron in that particular energy state essentially. This hole is absence of electron in that particular energy state, and this will look like a positive energy particle but with opposite charges. But opposite sign of electric charge. Okay, but opposite sign of the electric charge. So this will, if there is, okay, this hole will look, but it has a positive sign, opposite charge, because this C is full of, it's completely full. So this will have a positive energy charge essentially. This will have a positive energy, and this will look, but with the absence of the electron will look like a positive charge. It like the presence of a positive charge. The absence of one electron will look like a presence of a positive charge, opposite charge, and this will appear in nature as a positive energy particle with opposite electric sign. Okay, so that means if there is a result, a photon of sufficient energy, it will create an electron as well as a hole. It will create an electron as well as a hole. Hole will represent it by E plus. Hole will represent it by E plus. Okay, this is a positron or a hole. Okay, now I'll elaborate it on in the next lecture, but before closing I want to say that positrons were discovered experimentally in 1932 by Anderson soon after Dirac's prediction. Soon after Dirac predicted this, I think soon after that Anderson discovered a positron like particle. We will come back again to this elaboration of this Dirac hole theory and the introduction of antiparticles, and we will continue studying interactions in this particular case essentially. So, but okay, so the basic essentials is that all the electrons in the negative energy states are completely filled up, okay, and that is called the Dirac sea. I will come back to the details in the next lecture. Okay. So, thank you very much, and I will see you in the next lectures.